All right, so what we did in our previous lesson is we were looking at the derivative at a specific point, okay? We were looking at the derivative at a specific point, okay? And what we want to do now is kind of what we were just talking about when we were going over the homework, and that is we don't want just at one point, but we want to actually get a new function, the derivative function, that will then allow us to plug in different values of x to get the slope at any point on the graph. Because we don't want to have to go through that whole limit process for every different point that we want the slope at. Okay? So as you can see here at the top, it says the definition of the derivative of a function. And this is really the one that you're going to want to memorize. Okay? It says f prime of x, that's the notation there for the derivative. You see the little blue prime next to f. That means the derivative of f of x. Okay, there's some other notation down here that we'll look at in a second. But it's the limit as delta x approaches 0 of f of x plus delta x minus f of x all over delta x. So notice instead of a particular value of c, we're using the general value x, okay, the variable x, okay? Now, the derivative can appear in a number of different forms, and you should be familiar with all of these different notations for the derivative, okay? As you'll see throughout the year, there are times when different ones are useful in different situations, okay? But you see we've got here the f prime notation that I just showed you. Here is the derivative of y with respect to x. That's how you would read this notation here. The derivative of y, where y is some function, with respect to x, okay? Another way of writing it would be if y equals f of x, you could just say it's y prime. Another way of writing it is if you don't want to call it y, you could say it's the derivative of f of x with respect to x. Okay? Or sometimes you'll even see it like this. You'll use a capital D to represent derivative. The little x means it's with respect to the variable x, and in the brackets is what you're taking the derivative of. That you see much less often, but it's out there, so now you've seen it. Okay, these first four are the ones we use much more often. Okay. Now, just to develop this, remember what we're doing here is that the derivative of y with respect to x is the limit as delta x approaches 0 of the slope, change in y over change in x. Okay? Change in y over change in x. So you have the definition that we gave you up there. That's also known as f prime of x. All right? So let's work through an example of this. Again, similar to what you were doing on your homework, but now instead of a particular value, we're going to come up with an expression, okay? Now, I'll tell you right off the bat that, and those of you who have played around with this a little bit in the past, you may know that the answer is going to be, what?
3x squared plus 2.
Yeah, it's going to be 3x squared plus 2, okay? There are rules for this that make it easier in the future, but for right now, we're going to learn how to use the definition. I always kind of called this like calculus's dirty secret or dirty trick, you know? They make you do these by definition for like a week in college, and then they say, oh yeah, now there are these rules. You could just, you know that problem that took you an entire page to do last week? Well, you could just write down the answer now. So let's look at how we would do this first of all, okay? So like I said, we have our definition here for the derivative, and I like to go ahead and figure out the f of x plus delta x over on the side. That'll save you some writing, because as you simplify it, you're not having to rewrite the limit and all the rest of this stuff over and over and over again. Okay? So over here, I'm going to find f of x plus delta x. And that's going to be x cubed. So now it's x plus delta x cubed plus 2 times x plus delta x. All right? Now, before I put this in the formula, let's simplify it. Okay? What do I have to do to simplify this? Expand it. All right? You remember your binomial expansion from last year? Pascal's triangle? If you don't, go back and review, because you're going to use it a lot. Okay? If you remember, when you have to expand a binomial cubed, you could use that the third row of Pascal's triangle. So it goes 1, 1, 1, 2, 1, 1, 3, 3, 1. Okay? So I know it's going to be a 1 x cubed plus a 3 x squared delta x. Remember the two variables? The first one starts at the highest exponent and counts down. And the second one starts without any of them and then starts counting up with the exponent. Is this coming back to memory? Okay. All right. So then it's going to be a plus 3x delta x squared plus delta x cubed. All right. So that is our binomial expansion there. And then we have the plus 2x plus 2 delta x. And you'll notice there are no like terms here that I can combine. So that is just this little part of the formula. Okay? And again, it's nice to get that in a nice simplified form without having to write everything over and over again. Now I'm going to go over here and I'm going to put it in. So x cubed plus 3x squared delta x plus 3x delta x squared plus delta x cubed plus 2x plus 2 delta x. Okay? Now, I am taking the limit as delta x approaches 0 of that minus the original function. So minus x cubed plus 2x all over delta x. Okay? Does everyone follow up to that point? Yeah. Are we okay? All right, so now I look to simplify whatever I can, okay? And I can simplify. I have an x cubed minus an x cubed, because I distribute the negative, right? And I have a 2x minus this 2x. And what do you notice about everything that's left over that didn't cancel out? They all have a delta x in them, okay? So check this out. We've got the limit as delta x approaches 0. And remember, the problem here is that if we just plugged in a 0, we'd get 0 divided by 0, right? Well, now I have a 3x squared delta x. And actually, I'm going to go ahead and factor out the delta x from everything that's left. Okay? So delta x, and now it's 3x squared plus 3x delta x to the first plus delta x squared plus 2. Okay? I pulled out the delta x, from all four parts, if you can see that, kind of. Okay? Now remember, the whole point of doing that is because there was a hole at delta x equals 0. So now I can cancel, let me get back to a pen. Now I can cancel the delta x with the delta x, and I have something that I can now evaluate for when delta x equals 0. So 3x squared plus 3x times 0 plus 0 squared plus 2, of course, is just a 3x squared plus 2. So we would say f prime of x is 3x squared plus 2. Okay? Are there any questions? Okay. Now, here's why this is useful. Before, I could find the slope at, say, the point 0, 0. I would have plugged in a 0 for c and done this whole process. However, now, what's f prime of 0? 2. I can simply plug in a 0 for x, and I get the slope at the point 0, 0 is a positive 2. Okay? But I could also do, say, the point 1, 3. Okay, the point 1, 3 is on the original function, but what is the slope at that point? Well, I just plug in a 1, and I get 3 plus 2 is 5. Okay? So this now allows us to find the slope at any given point very, very quickly. Okay? And what's even more useful is later on we're going to find when this derivative will equal 0, if it ever equals 0, and there are certain features about the original function that we can find as a result. Okay? All right, let's try one more example here. Okay, here we have the function, we want f prime of x for f of x equals the square root of x. Then find the slope of the graph of f at the points 1, 1 and 4, 2. And discuss the behavior of f at 0, 0. All right, so we have a couple of different things that we're going to do after we find the derivative. But let's go ahead and find the derivative first. We have our definition up here. What is f of x plus delta x in this case? Yeah, this one's actually pretty easy. It's just square root of x plus delta x. There's no simplifying really here that can happen. So we're going to take the limit as delta x approaches 0 of square root of x plus delta x minus the original function, which is just square root of x, and that's over delta x. How do we find the limit here, since we get 0 over 0 if we plug in 0?
Conjugate.
What?
Conjugate form.
Multiply by the conjugate form of that numerator. We're going to rationalize, in this case, the numerator to get rid of the whole. Okay, so I'm going to multiply this by radical x plus delta x plus radical x over itself, radical x plus delta x plus radical x. And our denominator is delta x times that radical x plus delta x plus delta x or radical x. The numerator, these are conjugates, so when I FOIL it, the outers and inners cancel out, so it's just the first term squared, which is an x plus delta x, minus the last term squared, which is just an x. So now I have an x minus an x, which cancels out to 0. Okay? Then I have a delta x is all that's left on the top, so I can now cancel that with the delta x on the bottom. Be careful here, some people were messing up on the test when you were doing limits, a limit like this. The numerator is not gone, it's 1. Okay? A couple people just like, the fraction disappeared and you ended up with this, okay? So now we have radical x plus delta x plus radical x in the denominator. And now I have something that I can simply plug 0 into. So it's a 1 over 2 radical x. Okay. 1 over 2 radical x. If you want to rationalize at this point, you can. Alright, multiply it by radical x over radical x, and that would be radical x over 2x.
Where'd you get the 2 from? 2 radical x?
Because if I plug in a 0, right here, this whole thing is just a radical x. So radical x plus radical x would give me 2 radical x.
Yeah.
So now to do what the problem wanted us to do, if I want to find the slope of the graph at the points 1, 1 and 4, 2, they want f prime of 1, and they want f prime of 4. So, if I do 1 over 2 times the square root of 1, that's a half. If I want 1 over 2 times the square root of 4, I get 1/4. And now what's happening as at the point 0, 0? Yes, our derivative is undefined. Okay? F prime of 0 is undefined.
Would we need to give a reason why it's undefined? Or just because it's equal to the denominator?
Well, the 0 in the denominator makes it undefined. Now, one thing that we're going to look at in the future here is that there are certain cases where a function, where the derivative is not defined. Okay? One of those cases is right here. What do you notice we have at 0, 0? An endpoint. Okay? We have an endpoint. So the limit doesn't exist, right? The right-hand limit would exist, but the limit as x approaches 0 does not exist. We have an endpoint, and that's one of the cases that we will see where the derivative is not defined. It's not differentiable. The function is not differentiable at 0, we would say. Okay, so let's take a quick look at this. Here's a definition. This is just a little bit of review. The tangent line with a slope of m. Okay, if you want to find the slope of the tangent line, you're going to find the derivative at that point. Okay. The slope of the tangent line to the graph of f at the point CF of C is also called the slope of the graph at x equals C. It's also given by f prime of C. Okay? Now, we do have instances where we have a vertical tangent line. Okay? So, we just saw a case where the derivative was undefined because it was at an endpoint. here's another case where the derivative will be undefined. We have a vertical tangent line, but it's not actually at an endpoint. It's just at a point where we're changing the curvature there, okay? Our definition does not cover the possibility of a vertical tangent line. We're going to have to learn things to be able to handle those separately. For vertical ones, we have to use this definition here, okay? If f is continuous at c, and the limit as x approaches 0 approaches infinity, or approaches negative infinity, okay, if we were to look at our previous example there, as x approached 0, that the value of the derivative would be approaching infinity, okay, as we approached it from the right. The vertical line x equals c passing through f of c is a vertical tangent line to the graph of f. For example, the function above has a vertical tangent line at cf of c. If the domain of f is the closed interval a to b, you can extend the definition of a vertical tangent line to include the endpoints by considering continuity and limits from the right for x equals a, or from the left for x equals b. So, if we know that the function is continuous, but for some reason we went ahead and defined some closed interval here from a to b, we could still consider the derivative at the endpoints, because we made kind of an arbitrary endpoint. Okay, so in that case, the endpoint would be we'd be able to get the derivative because we had just kind of cut off the rest of the function. If the function itself has an endpoint, then the derivative won't exist. Okay, or will be undefined. For f of x equals radical x at 0, 0, the slope is undefined. F is not differentiable, but the graph has a vertical tangent. Okay, here's what we just found. And you can see here, again, that if we plugged in 0, that derivative would be undefined. But if we were to look at the graph, we have that endpoint and it goes like this. You'll notice the tangents, as I come from the right, the slope of my tangent is getting greater and greater and greater until at the end, or as we get closer and closer to 0, it's becoming vertical. Okay? So the graph would have a vertical tangent. Okay? Does that make sense?
Yes.
All right.